16 is about refrigeration and air conditioning. Modern life depends on these technologies. Can you imagine food preservation 100, 200 years ago? They didn't have refrigeration. And they had ice, so they could use ice, and we'll get to using ice as refrigeration. But mostly, you had to have fresh food, and that's what you use. So we have food preservations, which we have with refrigeration and freezers. And we have air conditioning that we really rely on in much of our life, working in office buildings, working in offices, at homes. And while I'm giving this lecture, the AC is on, so I'm not too hot and cranky. And so what we started off with in chapter 7 was the reverse Carnot cycle. And this is just to bring back this memory. And so we had on the TS diagram we had T low, T high, and from 1 to 2 there was heat in. So this was heat in at a low temperature. We have 3, 4. And we have heat out at a high temperature, TH, and we had something called the coefficient of performance, and we had it for both heating and cooling. So when the desired effect was cooling, we had the COP for cooling. When it was desired effect was heating, we had the COP for heating. So the COP for cooling is TL over TH minus TL, and the COP for heating is TH over TH minus TL. So we had this as our model. Now the Carnot cycles are not used. What we're going to look at is a vapor compression system, and let me show you what the ideal vapor compression system looks like. We're going to have a condenser. And we'll go through all the components. And so what we have here is, here's the evaporator. This is at your low temperature. So this is at your low temperature with 1, 2. And this is where heat in occurs. And this is where heat out occurs. And this is a throttling valve. So we have a throttling valve, and that's going to reduce the pressure and drop the temperature. So we'll look at that. And when I look at this on a TS diagram, so we have the evaporation at constant pressure and temperature ideally. This state 2 is a saturated liquid, isentropic compression, constant pressure cooling, saturated liquid here, and this is your drop through the throttling valve. So this is your constant enthalpy process. And so what we have here is that we have state 2 is a saturated vapor. State 4 is a saturated liquid. Process 2 to 3, S equals C, and process 4 to 1, H equals C. So the throttling processes are this. And so what we want in terms of refrigerants, and there's a discussion of refrigerants in the text. So what we want in terms of refrigerants is something that has a low temperature at or above atmospheric pressure. So for a refrigerant, we'd like a low temperature evaporation at or above atmospheric pressure. And the reason we want this is that if I have a temperature below freezing, and if the pressure in here were less than atmosphere, there'd be a chance of air leakage in, and air has water vapor in it, and then the water would freeze, and I'd have ice forming in this environment. And it would particularly form as the pressure dropped here and the temperature dropped. So what we're going to do is then we want to be, for this refrigeration system, we want to be thinking about how we measure the heat in. That's the desired effect that we have. So we have the desired effect of the heat in. So would be Q dot N. And the initial refrigeration, as I mentioned in the beginning, came from melting ice. So if we look at melting ice, and we use that as our basis of measurement, then if I melt 1 ton of ice in 24 hours, how much energy would have to go in for that to happen? And so the latent heat of ice is 144 BTUs per pound mass. And again, in this chapter, we'll be using the English units because that's what industry practice has us do. And so if I look at 144 times 2,000 pounds, 1 ton is equal to 288,000 BTUs. So that's the BTUs, and it's going to be removed in 24 hours. So 1 ton is equal to 288,000 divided by 24, which is equal to 12,000 BTUs per hour. And this is equal to 200 BTUs per minute. So when you go and buy an air conditioning, you'll see it's a 12,000 BTU per hour unit. They're saying it's a 1 ton unit. If you have central air and you're talking about you have a 2.5 ton unit, a 3 ton unit, it means that it can remove this amount of heat. So that becomes the Q dot N that's going into the system. So that's where that comes from. And interestingly, well, I find it interesting because I was from New England, but in New England and perhaps other parts of the country, but in New England in the wintertime, the farmers didn't have anything to farm, so what they farmed in the 1800s was ice. And so there were ice houses, and they would go out with saws and horses and cut chunks of ice, put it in, and then ship it initially to the south, and then much more as the cities in the eastern seaboard increased in population. People wanted ice in the summertime, so there was a business involving selling people ice that they cut in the winter back in to the people in the city. And what happened in the early 1900s, the vapor compression system that I showed you came into being, and so by the early 1900s, sawing up ice was no longer profitable because people could make it more economically with the vapor compression system located where the people were. Now let's do an example of this ideal system, and then what I'll do is change the ideal system to reflect the actual system. So we'll have 20 tons of refrigeration, We use R12. We all know that R12 isn't around now in the United States. It is in other countries, but that's a substance we have, that ammonia in the tables. We're going to be operating between minus 20 degrees Fahrenheit and 100 degrees Fahrenheit. So those establish the upper and lower limits that we have on this. So I have the condenser, and this is going to be at 100 degrees Fahrenheit. I'm going to have the evaporator. This will be at minus 20 degrees Fahrenheit. Have the throttling valve and the compressor. And I try to use a consistent numbering system so that each time I start with the evaporator, and this is where number 1 is. And so when I draw the TS diagram for this, so we have the TS diagram that accompanies this. And now we have to look up the properties in the tables. H2 is equal to H sub G at minus 20 degrees Fahrenheit, and that's equal to 75.11 BTUs per pound mass. S2 is equal to 0.7102. P3 is equal to Psat at 100 degrees Fahrenheit. So this is your 100 degrees Fahrenheit. This is your minus 20. And so if I look that up, it's 131.86 psia. And we don't have tables for that. So for our purposes in this course, pick the nearest table that we have, and that is a pressure of 125. So that's where I'm going to look things up, and we'll see in the superheat region, I can then find that S3 is equal to S2, and H3 is about equal to 91 BTUs per pound mass. And H4 is equal to H sub F at 100 degrees Fahrenheit. So that's equal to 31.1 BTUs per pound mass. And H1 equals H4. And now what we do is we go through and we do an analysis for each of these systems. And so what I'll do is then go in and find the heat in, the power, the heat out, and all that type of stuff. So I'll leave this diagram that we can refer to, but I'll erase the other stuff. So if I do a first law analysis on the evaporator, so I start with the evaporator. First law, I have Q dot plus M dot H1 is equal to W dot plus M dot H2. There's no work done, so Q dot is equal to M dot times H2 minus H1. And we know what the heat is because we're told it was 20 tons. So I have 200 BTUs per minute per ton. Times 20 tons is equal to the mass flow rate times 75.11 minus 31.1. So we get that the mass flow rate of the refrigerant is 90.9 BTUs per pound mass per minute. And Qn little qn is equal to 44 BTUs per pound mass. So this value right here is the heat in per unit mass. Now if I do the same analysis on the compressor, we have Q dot plus m dot H2 is equal to W dot plus m dot H3. In this case, it's reversible adiabatic compression, and we see that W dot is equal to m dot times H2 minus H3 is equal to 90.9 times 75.1 minus 91. And this term here is 15.89. So I have, this is W net. And so I have that the power is equal to 1444.4 BTUs per minute. And there are 42.4 BTUs per minute per horsepower. So W dot is equal to 34 horsepower. So that tells me that the power I have coming in here, I'm going to need that amount of horsepower. And if I want it in kilowatts, you can do that, it's 25.4 kilowatts. Then I can find the COP for cooling. COPC is equal to Q dot in over W dot net is equal to little qn over small w net. Most often when we do large problems and we have large mass flow rates, etc., we tend to do the cycle analysis per unit mass, and then at the very end correct for including the mass flow rate when we want actual sizes and conditions. So very often we'll be using these values. It's the same thing, the difference is the mass flow rate, but the numbers are smaller. And so the COPC is equal to 44 over 15.89 is equal to 2.77. Now, one of the things that for compressors, so this gives us the COPC, compressors are rated by the volume flow rate going into them. So V dot 2 is used in compressor sizing. So let's find this. Later on we're going to look at compressors and we'll see where that comes out and we can figure out the board stroke and things like that. But right now V dot 2 is equal to M dot times V2. And V2 is equal to V sub G at 2.4321 cubic feet per pound mass. So this V dot 2 is equal to 221.1 cubic feet per minute. So that's the volume flow rate that the compressor has to handle. And we want to be able to use that later on. And now what we want to do is transition to an actual cycle. So this is the ideal vapor compression cycle. And we saw what it looked like. We can take the same diagram, but we're going to change some parameters. So if I look at the actual cycle, we're going to have superheating at state 2, and we're going to have subcooling at state 4. So what happens with the superheating, and we'll look at a TS diagram showing this, but what happens is the compressors do not like liquid going into them. They like to compress a vapor or an ideal gas. So I want to make sure that the substance here, the R12, has been totally evaporated. So we superheat it slightly, about 10 degrees Fahrenheit. And similarly, for the throttling valve, you don't want to have any bubbles occur before the fluid enters the valve. If that happens, then the fluid increases by about 1,000, and so then you don't get any flow rate through the valve. So we want to make sure there's subcooling going in here, so we can't get any flashing before the valve, and we want to make sure there's superheating here so that we don't have any liquid droplets being pulled into the compressor. So if I look at a TS diagram with this, so I'll start. So I'll start here, and here's the ideal. And then we're going to subcool it a little, so it drops down, subcool, and here is for actual. And so what happens, because of the subcooling, I'm going to have a gain in the refrigeration effect here. Qn increases because it moves further over here. There's more to evaporate. Now we're going to have superheating at state 2. So we saw that this was the ideal place, and now we're superheating it, and this is to superheating. And we go to 3. So we have, in this case as well, we have a gain in the refrigeration effect. So this is Qn increases as well because the refrigerant is longer in the evaporator, it's gaining more heat. However, the work increases, so this area, W net increase. And we'll do an example where we put in some numbers and we see what it is, but basically the work increases faster than the benefit from the heat gain. So we get more heat gain, and the COP, which is Qn over W, the W increases faster, so it drives the COP down. So now let's take the last example, and I'll add this 10 degrees, etc.